Hello everyone, my name is Mark Howard, I'm from Regen, and today we're going to run through a bit of a 101 on heat pumps, sort of a bit of the detail of how they work and the sort of part they might play in helping decarbonise heat in the UK. So the context is obviously we have a climate emergency and we have a net zero commitment. That means that all sectors, including heat, need to be almost entirely decarbonised. And heat is still very high carbon. 80% of households rely on natural gas, and we can't continue to burn natural gas as we move towards net zero. To date, we have had various policies that have tried to improve energy efficiency in our homes and increase the use of low carbon heat. Some of those policies have been a bit stop-start and perhaps not achieved quite as much as we had hoped. So the political rhetoric is slowly aligning with recommendations from the CCC. The 10-point plan targets 600,000 heat pumps a year by 2028 from the current 30,000. And we're due a heat and building strategy from BEIS soon, which really needs to address the current policy gap we have between the mechanisms that are allowing us to install 30,000 heat pumps a year rather than 600,000 a year. It's a mixed challenge that we have with decarbonising heat. It's an infrastructure challenge, but it's also a people challenge. Because we have about 30 million buildings that we need to make changes to decarbonise the heating systems. At the moment, we have low carbon, low building standards, an ageing building stock, one of the oldest building stocks in Europe, relatively cheap and convenient heat from the gas network, high levels of fuel poverty, quite a lot of health issues associated with poor housing in certain sectors, and we have high carbon emissions. And we need to move towards the highest building standards, improved building fabric, and affordable, convenient and low carbon heat supply. Along with this, we need to eradicate fuel poverty quite clearly, as well as working towards net zero carbon emissions.
The upside, as far as heat pumps are concerned, and in terms of sort of transformation, is that in the last decade, grid electricity is decarbonised by a significant amount. So you've got the sort of 2009 data here and the 2020 data here. So electricity is significantly decarbonised in the last decade. Gas has decarbonised a little bit with the introduction of biomethane, but on nothing like the same trajectory. So consequently, whilst a heat pump 10 years ago was a bit lower carbon, and direct electric heating was considered quite dirty, we're at a point now where direct electric heating is actually, if you heat at the right time when grid intensity is low, it can be lower carbon than gas, and heat pumps are certainly a lot cleaner than gas. So that's sort of the upside. At the moment, as I said, almost everyone uses gas. We kind of have gas as a universal fuel, and that must come to an end. We can't combust it at the point of use anymore. So you're not going to be able to do carbon capture if that was possible at the point of use in 30 million buildings. So a massive technological shift is needed, whichever future scenario we have. And in any of those future scenarios, we have a lot of heat pumps. So even in the system transformation, high hydrogen FES scenario, we've still got over 8.5 million heat pumps anticipated compared to our 200,000 heat pumps that we have at the moment. So with heat pumps, it's kind of they might not be the answer for everyone in every situation, depending on your future scenario, but in all of them, there's going to be a lot more heat pumps than there are now. So we need to have a sort of good understanding of how they work and where they work, and how they might best be deployed. So I will jump from that straight into what's a heating system, how does it work? And I'm sort of going into this detail because I think often with heat pumps, you have this sort of mythology around, people talk a lot about heat pumps and you get often the sort of, oh, well, a heat pump only works in a modern new build, doesn't it? And that's not strictly true. And I think that just comes from you kind of get the output ideas about heat pumps without a great knowledge of how they work and what leads to that. So what I'm trying to do in this session is give a bit of a base understanding of heating systems and how they work, and therefore understanding the sort of challenges and constraints that you get around different types of heating system. So what we've got here is a typical heating system in 2020. So we get some fossil fuels, and we pump them out of somewhere, and we either store them in an oil tank or we have them in a gas pipe. We put them in a box and set fire to them. And out of one end, we get flue gases. So we get our carbon dioxide, which is what we're worried about mainly, but we also get a lot of other products of combustion that are problematic from an air pollution point of view. And I think that's increasingly going to become a significant part of the sort of transition challenge, and the benefits of heat pump is looking at local air pollution. The other thing we get is we warm up some water. So we heat up water in a boiler. Traditionally, we'd heat it up to about 82 degrees, which I think is a Fahrenheit thing. I'm sure it converts more sensibly in Fahrenheit. And we pump that whole hot water around a system to a heat emitter, which is normally a radiator, but could be an underfloor system. Underfloor heating basically being a big radiator on its side. And that warms rooms up to 21 degrees, and in that process loses 11 degrees C and goes back to the boiler, gets warmed up and pumped around and round and round and round. That's sort of the basics of how a heating system works. Since the mid-90s, we're supposed to be installing condensing boilers in every house when you replace a boiler, and mostly they are, but there are exceptions. This ideally should be pushing flow temperatures down to a 70-degree flow and a 50-degree return for a condensing boiler to actually condense. There's a lot of question marks over whether that actually happens in reality, and most people think that condensing boilers typically only condense for about 5 minutes when you first turn them on, because system design hasn't really kept up with that technology, and there's no regulation to actually make people make boilers condense. That's pertinent to this issue because flow and return temperatures are really important when it comes to heat pumps and the future of heat. So that's our sort of basic system at the moment. If you want to get to those lower flow temperatures, you can basically upsize your heat emitters by putting in larger radiators, which doesn't need to mean physically larger in the sort of face-on view. It could be doubling up or tripling up. So if you look at these as a head-on view of a radiator, as a way of helping reduce flow temperatures. System balancing is something that's largely ignored, but is really important, and can make a big impact on system performance and getting lower flow temperatures. And the other option is to reduce your heat demand. So if you insulate a property, reduce its heat demand, it can help you lower those flow temperatures as well. So those would be things that we should be doing already anyway to get condensing boilers to condense. And that may or may not be happening because there's no regulation really to drive it. So that's the basis of a heating system. In 66% of homes in the UK now, we have instant hot water from our boilers. So that'd be a combi boiler, combination boiler. So you turn on the tap and it flips over to do instant hot water, and that produces it to the tap as and when you need it, and then turns it off again. And that's an ongoing trend. So historically, anyone who had hot water would have had stored hot water. So you would have had a cylinder cupboard, and your hot water would have come out of that cylinder. But with the sort of rise of combi boilers, people have been freeing up space in their houses. They're cheaper to install and maintain. We've been losing, the guy from Bays, I think, said the other day that we've been losing hot water cylinders about 300,000 a year, which is pretty significant for heat pumps because heat pumps need a hot water cylinder. So you need that space and that setup. In the rest of our homes, you have this cupboard full of pipes and a hot water cylinder where you store your hot water. And so that means that the boiler will heat the hot water up at some time of day, and then you draw it off as and when you need it. Typically, people heat them up once a day. And again, that becomes significant if you start to care about peak demand. So in this system, the gas network must see quite significant peaks as people turn on their boilers to have showers in the morning or at the end of the day, but they don't really care about it because their systems are quite flexible. If you try to do that in a more constrained system, it would be problematic because making hot water instantly pulls a lot more demand. So the important things to understand about a typical heating system and a fossil fuel heating system is that boiler systems are really robust. I've got a chart later that sort of demonstrates this, but a boiler will work at sort of 90-odd% efficiency, almost regardless of what you do to it. And they're really cheap to oversize. So doubling the size of your boiler in a domestic situation might add £100 to the price. So you can sort of use rules of thumb, put in a boiler that's too big. If it has to run at 50% of its load all the time, it doesn't have a massive impact. And they can deliver a lot of heat really rapidly, which means that they can mask issues such as poorly sized radiators or poor system balancing or a drafty house. So all of those things mean that if you don't do a really sort of careful job of specifying, installing and setting up a fossil fuel system, the consumer experience will probably be okay. It might not be perfect, but their comfort and their fuel bills are likely to be acceptable to them. And so that's not to sort of cast aspersions on the industry. It's really just a product of what people can do. People ultimately, most heating systems are installed by sole traders or sort of 4 or 5 people companies, and they're all running on a tight budget, and they will do what they have to do for their business to work. So yeah, fossil fuel boilers, you can get away with quite a lot. And one of the issues with heat pumps is that they're a lot more sensitive to all of these things. So taking that same sort of system architecture to understand what a heat pump is, a heat pump is a way of upgrading low-grade environmental heat and turning it into a sort of a useful temperature. So in this case, our fuel is electricity from the DNO, and we take low-grade environmental heat. So there's energy in everything down to absolute zero, so -273. You can extract some energy. So with heat pumps, we can extract energy from as low as -25, and you can upgrade that and turn that into useful heat via the sort of vapor compression refrigeration cycle. And I haven't gone into the details of how heat pumps work here. It's not that exciting. It's not super necessary to understand it. We all have heat pumps in our houses already because we all have fridges, and a fridge is a heat pump just working in reverse. So if you put some warm food in a fridge, it will extract the heat from that food, cool it down, and it will kick that heat out the back. So if you put your hand down the back of a fridge, there's a sort of a wire grid on the back, which is basically a radiator, and it's giving out heat. So we've all got a heat pump, and they just sit there and do their job. So that's, I think, it's almost obligatory that I say that any heat pump presentation I've ever seen includes that fact. So yeah, the ins and outs of how a heat pump work. It's electrically driven and it upgrades heat. You can sort of go and look up the vapor compression cycle, but you don't really need to understand it to understand how heat pumps are applicable in the domestic setting. But yeah, they're typically driven by an electric motor. You can get heat-driven heat pumps. So in caravans, you get gas-driven heat pumps. But again, they're pretty niche and they're unlikely to be applicable in a domestic setting. Why we're interested in heat pumps is because they can deliver up to sort of 6 kilowatt hours of heat for every 1 kilowatt hour of electricity that you put into them. So that means that for a kilowatt hour of electricity with maybe 200 grams of carbon attached to it, you could get 6 kilowatt hours of heat. So you can get very low carbon heat as an output. And that's one of the reasons that we're really interested in heat pumps as part of our approach to decarbonising heat in buildings. So the way we measure that efficiency is you come across a few different terms. It's about the ratio of electricity input versus heat output. So as I said, you could put a kilowatt hour of electricity in, and you could get 3 kilowatt hours of useful heat out of the other end. And the ratio that we would talk about there is a COP of 3. So that'd be a coefficient of performance. You'll hear COP, SPF, and SCOP talked about with heat pumps. Usually it doesn't matter, but in some situations it is important to understand which is which. So COP is like the instantaneous now measurement of what a heat pump's doing. So it's 5 degrees outside and the heat pump's performing at this flow and return temperature. Its COP is 2.8. The SCOP would be the seasonal coefficient of a performance. So that would be how a heat pump performs in a certain system over the course of a year. So you might have an SCOP of 3. And on a cold day, it might be a COP of 1.2, and on a warm day, it might be a COP of 5. But your SCOP would be 3, something like that. SPF is very similar to the SCOP, but SPF broadens the boundary of what you're talking about outside the heat pump, and you get SPF H1, H2, H3, and H4 I think, which is basically broadening that boundary to include the ancillary equipment around a heat pump, which is usually more significant in commercial situations, but it can be significant if you're looking at how a heat pump performs and it has an electrical backup heater. So an SCOP might just talk about the appliance and how that behaves over the year, and might ignore the fact that you've got a 9 kilowatt backup heater attached to it. So then you'd want to be looking at the SPF, and I think that would be the H2. Anyway, you can look up the details again, but it's kind of important to be aware when you're like looking at these things to understand what people are quoting at you, because it's obviously, if there's lots of things that you can quote that sound the same, then some people will quote the things that favour them most. So it's useful to be able to sort of pick away at that. Yeah, that's the overall thing with heat pumps, is how we measure their efficiency. So system temperatures are typically lower than with boilers, and with a lower differential between them. So a typical heat pump might want to operate at a 45-degree flow temperature with a 40-degree return. It doesn't have to operate at that, but that's how they're happiest. And that's why you often get this like, oh, heat pumps only work with underfloor heating or as background heat, because we've all become used to, and we've designed our infrastructure around combustion products that give us, close to boiling point water, which isn't the case with a heat pump. So heat pumps can do really high temperatures, but they're happiest at the lower end of things. As I've said, stored hot water is the only option, and that is kind of significant because we've only got stored hot water in 34% of our homes at the moment, which means if you put in a heat pump, you need to find space if there isn't stored hot water already. I've put a little star next to that because someone might shout hybrid heat pumps at me. I haven't done anything about hybrid heat pumps in this presentation because it's sort of a whole tangent, but it's something that we could talk about at the end if people want to. So as I already mentioned, to sort of work with these lower flow temperatures, you might look at your heat emitters, you might have to look at building insulation, but that's typically how a heat pump works. I'll go into the breakdown of sort of different types of heat pumps. So an air source heat pump, when we're talking about air source heat pump, we mean an air to water normally. So it's taking energy from the outside air and putting it into a wet heating system. And you basically get an outdoor unit, which is the size of a boiler, or maybe a larger, depending on the size of the property. So this is a sort of typical EcoDan, should be up to like 9 kilowatt. And this would be a larger dual unit. So you do maybe 12, 16 kilowatts in a domestic setting. That's maybe 5 foot high. You have that unit, and that's basically just forcing outside air over a heat exchanger, same way that a car radiator works, and it's pulling heat out of that air. So if it's 10 degrees outside, it might cool that air down to 5 degrees, and it's using that energy it's extracted to upgrade it, pump it into the heating system. You get a couple of different types of these. Typically you get a monoblock system where you just have an outdoor unit and that connects straight into the heating system in the property. Sometimes you get what's called a split system, where you have an outdoor unit, refrigerant gas pipe work, and then a separate indoor unit, and then out of there connections into the heating system. They're not super common, but they do come up now and again, and it's worth being aware that that's a thing. Pros and cons to both of the different approaches I won't go into here. Here's a bunch of pretty pictures of air source heat pumps, or arguably not pretty pictures. So one of the issues that BEIS have flagged with their heat pump demonstration trial is that I think 1 in 16 of the people involved in the trial so far have said that they really don't like the look of heat pumps. They're not a nice thing to have in your home. And these are the keen early adopters. So that's one of the challenges, I think, with heat pumps outright, is mass adoption will be people getting used to having a bit of industrial equipment hanging around in their garden. So this one in the bottom left is sort of typical of heat pumps to date. These pictures are kind of people trying to make them a bit snazzy and nicer by making them grey and black, like we're doing with all our UPVC windows at the moment. You get some really weird designs, which I'm not super keen on, but people are trying, I guess. And then over here in the corner are a couple of examples from Energiesprong in the Netherlands, where I think that's the happiest I would be with a heat pump. I really like this one. It's a heat pump dropped into the roof of a new build, because I quite like the sort of chimney analogy that's going on there, and it gets out of the way. And this is an example of an energy module where they've got a sort of containerized heat pump, and the heat pump's just up there, but it's just been screened and hidden and bolted in with all this other stuff. So that's an example of the sort of thing we're actually talking about. And up here is sort of internal gubbins that you might be likely to see with an air source heat pump installation. There we go. So there's some real stuff. So we're talking about ground source heat pumps. They come in two different varieties, which are sort of categorized by their ground arrays. So you're extracting low-grade heat. Instead of pulling it out of the air, you're pulling it out of the ground. And there's two different approaches to doing that. So there's a horizontal slinky array. So you've literally just got hundreds of meters of plastic pipe, which is the same as the water pipe that our water comes into our houses in, filled with antifreeze and water, and it's just sucking heat out of the ground. Horizontal arrays are great if you're building a house in the countryside and you've got ground workers on site already, because you don't need anyone particularly skilled to do this. You need someone who can drive a digger and some people who can chuck pipe in the ground. But it takes up a lot of space, and most people don't have this kind of space attached to their property. So vertical boreholes are much more common, more expensive because you need specialized drilling rigs. They drill down 100 or 200 meters, but that's the more sort of typical space constrained approach, because you can put one of them every 5 meters. I think 5 meter centers is typical, and that could heat a home. Whereas with the horizontal arrays, typically you'd have, I think, 50 meter long arrays, and you'd have a couple of 50 meter long trenches for a typical house. So those are the sort of two flavors in which they come. Either of them connect straight into a heat pump. They can be shared between multiple buildings, which is what our recent heat pump paper talked about. And then they connect into the ground source unit, which can either be within a property or it can be in an outdoor building or a sort of utility space. I put up a few photos of ground source heat pumps here. And partly, I think what's interesting to talk about ground source heat pumps is that if you search for pictures of ground source heat pumps, you'll largely see these sorts of things at the bottom of the screen, these sort of like quite intimidating looking giant plant rooms. The reason for that is that typically ground source heat pumps just get installed in big rural properties at the moment, and often, very, very large new build rural properties, because ground source heat pumps are a lot more expensive at the moment because of the way that we fund it, that you have to fund your own sort of infrastructure for the ground array as well, and because ground source are quite a niche industry, so their capital costs are higher and their installation costs are higher. What you tend to see when you look for ground source heat pumps is these big plant rooms type installations, and you think, oh well, that's not going to go in a normal house. You can, so this is a Kenza shoebox, so that's a 6 kilowatt, I think we do a 6 and a 7 kilowatt on a 9 kilowatt in the shoebox. So a ground source heat pump is pretty small and can be installed in a normal house. You don't need a giant plant room to do it, and it's worth being aware of that again when you're sort of looking at ground source stuff, is that I guess what we've done in the past isn't necessarily what we'll do in the future. And I didn't really think about that until I put these pictures together. I was like, why are all these? These are all like 15, 20 kilowatt ground source heat pumps that will be serving new build houses that are about 400 square meters, which is more than 4 times the typical property size in the UK. So yeah, they're not necessarily representative of where you might see ground source in the future or where you could put ground source. It's just where we put ground source at the moment. There's a little drawing that I dropped in really just to sit in the slide pack, because it's kind of a useful overview of what I've just explained. So if you have a typical monoblock air source, sits outside, connects into a heating system. If you have a split system, sits outside, refrigerant pipe work, another box into a heating system, and a ground source sits outside or inside, connects to a ground array and into a heating system. Yeah, kind of a reference picture there, really. So your practical considerations, stored hot water. If you've got stored hot water at the moment, it makes life easier because pipe work's in the right place and there's a cylinder there. You have to change a cylinder for a heat pump specific cylinder anyway, so a normal gas or fossil fuel boiler cylinder wouldn't be appropriate, but it's useful to have the space. If there isn't one already, then it can still be done. It's just might be a bit more challenging, a bit more work to route pipe work around. or find space. You know, even you can get horizontal cylinders, so you can put them in loft spaces or eave spaces, only in the really, really space constrained small sort of flats, I suppose, that you might not find space for a hot water cylinder. There's usually a way. If you're looking at air source heat pumps, obviously you need to find a suitable external location for the unit. So that can depend on size. It can depend on access as well, because they weigh typically 100, 150 kilos, which is about 3 or 4 times the weight of a gas boiler. So you've got to be able to physically get it to the place that you need it to be. And sound levels are an issue with air source heat pumps. So they're not noisy per se, but they do make a noise. They are permitted development if you locate them in such a way that they're less than 42 decibels at the nearest neighbour's opening window. So there's sort of a whole sort of set of guidance around that. And I know that in the Bayes heat pump trial that they're running at the moment, they've had some issues in accommodating that within some mid-terraced homes. It can be a bit hard if you're trying to find not just a space for a heat pump, but also keeping the sound levels acceptable to neighbours near their openable window of a habitable room. So you basically don't want your neighbours to be kept awake at night by your heat pump humming away in the middle of the summer.
Surely you don't want to be kept awake yourself either.
No, that's true. But yeah, I guess it's kind of because it's under planning, it's sort of your own fault if you keep yourself awake at night, I suppose. So that's sort of like the planning guidance is about protecting your neighbours, and it's your choice about whether you keep yourself awake at night, and that is something that people need to think about. So when I was back selling and installing heat pumps in my former role, we would always insist people went to see a heat pump that we'd already installed, to partly to see it and understand it, and partly to listen to it. Because combi boilers make a noise. If you stand outside, the boiler flue makes a noise, and it's sort of comparable to some quieter heat pumps, but it's a different quality of sound. And some people really struggle with the quality of sound of a fan whizzing round and a compressor humming, and some people don't. So it is a consideration. So either in, I guess, really rural locations, people might find that problematic, but also in built up areas, if you get a lot of them, it could be problematic. And so that's sort of one of the arguments, I guess, for the idea of sort of shared ground array ground source heat pumps, is that you wouldn't be in urban areas. That's a way of not creating that sort of external noise pollution. Units are getting quieter and quieter. They are getting better, and can be screened, I think, to reduce them. So yeah. Considerations with ground source heat pump is obviously, have you got a ground or a water source? Most people don't have a giant garden or a lake to put their ground array in. So it's is there somewhere that you can actually use? So 50% of dwellings in England are flats or terraced houses, so they probably don't have a suitable location for a ground array. They might have garden space, but it might not be big enough. So yeah, that's one of the considerations with ground. And then is there a suitable location for the unit? So you do get a bit of vibration off the units. I think in that previous photo I showed the little Kenza unit in a cylinder cupboard up there, and you can do that. You'd probably put it on a rubber mat, and then it's not that dissimilar to having a washing machine in an upstairs cupboard. Units like this you definitely want on a concrete floor outside of your main living envelope, I would suggest. Another consideration is obviously the electricity supply. Will the DNO let you connect a heat pump? So in theory, it's quite straightforward to connect a heat pump, and the DNO shouldn't cause a problem. But in my experience, certainly in rural areas, you can run into a lot of problems. And I know that the ENA have done a lot of work to try and simplify that process, but it's still not that smooth and does still cause quite a few problems for quite a lot of projects. I thought that had changed a lot, but recent conversations with installers has informed me that that's not so much the case. So going back to my sort of slide earlier about boilers being really robust and kind of almost indifferent to what you do to them, heat pumps are kind of quite converse. So you can serve any building with a heat pump. So you can serve, you know, a granite building in the middle of Dartmoor that's got, you know, needs a high temperature heat system. You can serve that with a high temperature heat pump, but it will cost more to run and it'll cost more to install, and you might struggle with the DNO depending on how big it is. So to optimize your capital costs and your operational costs, you should try and minimize your building heat demand. So heat pumps are expensive per kilowatt. So if you jumped from a 5 kilowatt heat pump to a 10 kilowatt heat pump, you wouldn't quite double your cost, but you could probably add at least 50% to the capital cost. So minimizing the size of your heat pump is really, really important. If you double the size of your heat pump, it takes up more space and it will make more noise. And the bigger the heat pumps, you can start to upset your DNO and either flatly not be able to install them or run into, you know, costs to upgrade the local LV network, which at present fall on the consumer. You should also seek to optimize system temperatures. So heat pumps are cheapest to run at low temperatures. So this is where you get that sort of myth that heat pumps can only work in new build. They work best in new build because they'll be cheapest to run and they'll be smallest. But you can run a heat pump at 80 degrees, it will just cost more to run. So that myth's kind of perpetuated by the fact that quite a few manufacturers don't make high temperature heat pumps. So they obviously aren't going to try and sell other people's products. They want to sell their product. So many units can't deliver anything over 50 degrees, 55 degrees. So the most popular air source heat pump is a Mitsubishi EcoDan that can only do 55 degrees, and it's not that thrilled about doing 55. It would rather do 45. The chart I've got over here sort of summarizes this big difference. So this is really indicative costs per kilowatt hour of heat that you get out of it, based on some sort of standard assumptions. But what you can see here with the grey line is the gas boiler. So if you run your heating system at 60, 70, 80 degrees, your gas boiler will cost you just over 5 pence a kilowatt hour of heat. If you do loads of work and reduce the flow temperature of your gas boiler system down to 45 degrees, you've shaved off like fractions of a pence there. So that's the difference between it not condensing up here and the boiler condensing down here. Is like, it really doesn't care. No one's going to notice. If you're on a typical air source heat pump at 60 degrees flow temperature, it's going to be costing you just north of 7 pence a kilowatt hour of heat. And if you run all the way down to say 45 degrees, that's where you've got to get to be compatible or comparable to gas running costs at the moment. So again, this is where you sort of tend to get that idea that heat pumps only work at really low temperatures and in well-insulated buildings. Is partly to do with the price of gas. So if you want to match gas running costs as things stand at the moment, you probably want to try and be running at 45 degrees. And that's where you get that thing from. So ground source typically, they're cheap to run per kilowatt hour. These curves can vary quite a lot. It's a bit like mileage in cars. It can really vary. Yeah, so that's kind of the most important things with heat pumps, and the difference between the heat pumps and the boilers is that they're not quite as robust, and that's why it all becomes a little bit more finicky and a little bit more challenging. So the summary really is, whilst you can do this, and I have done this, installed, I was trying to find a picture of one that I'd done, but I've installed air source heat pumps in almost identical buildings out in the depths of Dartmoor with no insulation, stone walls, drafty as ever. That's fine and that will work, but they'll probably get an SPF of like 2, where you could get it up to 3. So whilst you can do that, you should first work on reducing heat demand, because that will reduce the size of the unit and it will reduce your operating costs. And you should also look at doing things like increasing the size of the heat emitters, which doesn't need to be more wall space, but will have a big impact on flow temperature. So this is like a top view of different types of radiators. Most old-fashioned heating systems would have this sort of heat radiator with none of the fins on the back, and they make a big difference. So radiator upgrades, I think, again, that's something that often gets talked about, is heat pump detractors would say, well, you need to triple the size of your radiators, which obviously makes it sound like you're going to cover your entire wall in radiators. And whilst you might need to make them physically bigger, often you don't have to, and you can get away with sort of doubling up or tripling up. To really get to the the best performance, you would go to this sort of K3 triple panel radiator. they're quite big and quite heavy, and these at the moment, these have a really big lead time. Speaking to an installer the other day, he was saying that that's the slowest thing with heat pump installations for them at the moment is like an 8-week lead time on radiators. So that whole process, whereas with a gas boiler swap, you'd like phone someone up and next week they'll come and do it. They were explaining the sort of whole process for an average heat pump install for them could be like 3 months, because they've got to, you know, go through the sales process and then go to the DNO and then wait for the DNO and then order the heat pump and the heat emitters and wait for it all to turn up. So yeah, it's kind of an interesting feature of, I guess at the moment, those are really niche, but those are your sort of key things to look at. So capital costs of heat pumps are kind of challenging at the moment if you're comparing it on a capex cost to a gas boiler. So your typical combi boiler down here is a few grand. If you're putting in a system boiler with a hot water cylinder, which is more of a fair comparison with a heat pump, you're at about £4,000. And so you've still got a really big leap to go up to an air source heat pump, slightly bigger leap for a typical ground source. And then on top of that, if you're paying for the ground array, which is the standard approach at the moment, you can see why we install more air source heat pumps than we do ground source heat pumps, and more gas boilers than we do air source heat pumps. Part of this is just the fact that the gas boiler market is really, really developed. So we do about 1.7 million gas boiler installations a year in the UK at the moment, compared to 30,000 heat pump installations. So just the supply chain there to sort of support all of the things that, all of the costs that go with that, it's just much more developed with gas boilers. And similarly, we've got 125,000 gas engineers and 4,000 heat pump engineers. So say base. I thought it was about 1,000, but they seem to think there's about 4,000. So that's interesting. Either way, we're, you know, scales away from the gas industry at the moment. So that's partly why things are so expensive, and there is a lot of scope for cost reductions. Part of the reasons heat pumps are more expensive is that there's more stuff in them. There's more physical equipment. So I said earlier, I think an air source heat pump usually weighs about 3 or 4 times what a gas boiler does. So if you just took that down to like, okay, that's half aluminium and half stainless steel, then your material costs are going to be significantly higher for a heat pump always. And then built into that as well, into the sort of price that you pay, is a cost of sale. So Kenza's favourite example that they cite would be that it takes them 9 labour hours to build a heat pump, and then about 30 labour hours to sell that heat pump. So the cost of sale is a big thing factored in at the moment. And if you compare that to gas boiler installations, whilst people like Worcester Bosch will spend money on marketing, the gas engineers are the people that do the sales. So that's who we all trust. If we need to change our heating system, the most trusted person, according to all the surveys, is the gas engineer. And the gas engineer recommends the boiler that they know how to install. So they're out there doing marketing. So there's 125,000 people out there doing marketing for the gas boiler industry, whereas the heat pump industry have to employ people to go out and do it themselves and then convince people to do something different. So that cost of sale is quite significant. So this is a chart we put together for the Kenza paper. This was sort of estimate of where we thought heat pump prices could go at mass scale, based on conversations and a bit of research that was done by Bayes and conversations with people in industry. Market scale, so we're talking significant scale here, so sort of millions a year, could bring cost reductions through manufacturing as well as sales and installation costs, but there's still quite a gap there. And what you'll see, the difference is that ground source have got a lot more potential to come down than air source. So that's because ground source is still really, really niche. There's about 30,000 heat pumps sold a year in the UK at the moment, and about 2,000 of them are ground source, and they're really, really small beer. Air source are typically mass produced by the same factories that make air conditioning units, which is a huge international market. So the scope for them to like knock down their prices is, the industry tells everyone, is a lot less. I mean, time will tell, I guess. So there's scope for those things to come down, and one of the points we were trying to make with our Kenza paper was that there is scope for sort of air source and ground source costs to become comparable if you could hive off the ground array cost as a sort of standing charge like you do with gas, and therefore if you lived in a terraced house and you didn't have much garden, if you could then choose between an air source or a ground source on capital cost terms, whereas at the moment you just wouldn't. But there's still probably going to be a need for regulation to phase out high carbon appliances, because on capital terms it's still really challenging. And on top of all of this, the social considerations, it's not just a technical problem. So whilst I spend a lot of time talking about and thinking about heat, most people don't. They might not know much about their gas boiler at all, or care about it. And gas is typically perceived as being clean by customers because we've had quite a few years of, you know, as I said at the start, historically electricity was sort of the dirty fuel because it was coal fired, and then gas was the clean fuel. And we've been marketed clean gas, A-rated, efficient boilers for a long time. And we still sort of got that mindset. And we're a nation used to our sort of leaky old houses that we just sort of whack a load of cheap heat into a couple of times a day to mask that fact. And so sort of the move to a sort of more sophisticated, nuanced heating system is going to be a bit of a challenge. And so bringing people along with that is really important. Getting people to understand and be on board with these things is one of the most significant things. And I think that's one of the biggest challenges, is that, like, how we make that desirable, socially accepted, sort of just a thing that people do. I think it's a really interesting challenge. I will take any opportunity to include this chart in any slideshow. So when we talk about energy efficiency improvement or decarbonisation of heat, we typically tend to look at, this is sort of all the benefits that you get with energy efficiency improvement. And we typically look at, like, how much is it going to save me in pounds a year? And we might talk about greenhouse gas emissions. And those are probably the main things that we think about as sort of benefits of doing an insulation measure or decarbonising our heating system. And we tend to ignore most of these other things. And one of the things I'm always trying to sort of get a handle on is like how we can bring these externalities in to that equation to help sort of weigh things in the favour of what we all know is probably the more sensible thing to do. So looking at things like local air pollution, or looking at things like employment that could be generated locally, looking at health and well-being. And we do think about poverty alleviation, fuel poverty a little bit. Bringing all these things in is, it's an important consideration. So examples are like thinking about comfort. So if you improve the insulation in a property, it's not actually just about saving you like £10 a year on your gas bill. If you improve the insulation levels in your walls, what you do is you raise the temperature of your wall. So the internal temperature of your wall is now higher. So when you stand next to your wall in the winter, as well as you saving £10 a year on your bill, it's less uncomfortable because you're not stood next to a surface that's 15 degrees and you've just got radiators chucking out air temperature, trying to combat that. If you bring it up to 17 degrees, it's a more comfortable place to be. So it's sort of those little nuances like that we don't really factor in at the moment, and we need to try and sort of get people to understand and factor into the sort of reasons why this is a good idea. And I often go back to the sort of double glazing argument, which is that like 80 or 90% of homes have got double glazing nowadays, which is generally classed as an energy efficiency measure, but it doesn't ever pay for itself. It takes 100 years to pay for a double glazing in energy savings. So if you just look at it in those really closed terms, why have we all got it? But we've got it because it's more comfortable and you get less drafts and it's more secure and it adds to the value of your property. So people do those things because we've sort of brought in some of those external benefits. And I think one of the issues with looking at energy efficiency measures, looking at low carbon heat, is that we often kind of ignore those other things, either because no one's told us about them or we haven't quite grasped them and they're not sort of valued in that system in that way. And that's, I think, one of the challenges that we need to work on. So what can we do now? So starting with the sort of the easy to convert homes is sort of the best thing. So early adopters, people with homes that are easy to insulate, easy to upgrade, already have oversized radiators, and owners with purchasing power. So a lot of this you'll see happening in social housing because they've got a lot of stock that they can make mass decisions on. And off-gas areas, there's obviously less uncertainty about whether or not there'll be hydrogen, because there won't be, because you're not on the gas network. So it makes more sense to work towards the sort of gas areas. I chucked in a couple of charts here to look at where people have put heat pumps to date, but I think, again, it's kind of important to think that that's not necessarily an indicator of where heat pumps will go or where is most optimal for heat pumps. It's just where, well, I don't know, actually. I was kind of interested just to look at it and say, okay, are detached houses more suitable for heat pumps, or do people in detached houses have more capital and they're more likely to buy a heat pump? Interesting point for discussion, I guess. I'd originally set out to do some sort of case study examples of, like, here's what you would do to this house, and this house. And I had too many slides and not enough time. So I would point you all at, if you want to look at sort of case study examples of, like, what would you do in a Victorian terrace? Carbon Trust did a really good report last year, looking at 15 different archetypes in London and how you would fit a heat pump to them and what that would do. So that report is worth looking at. The sort of evolving policy framework around this is directly stolen from Bayes, is that the RHI has been and gone for the domestic sector. We've got a proposed clean heat grant of £4,000 a year, an installation that they're saying that they'll run from 22 to 24. And beyond that, a market mechanism. I don't know what that will be, but I've seen a couple of people from Bayes speak recently and talked very clearly about moving away from the blunt instrument of grants towards a market mechanism. So it'll be interesting to see what comes out in heat and building strategy there. There's ongoing support for the least able to pay sectors under ECO, Social Housing Decarbonisation Fund, and the new Homes Upgrade Grant, which is, they're all sort of largely low income and fuel poverty focused. From a regulation perspective, we've got the Future Home Standard for new build, Future Building Standard, which will have some impact for retrofit, private rental MEES, and then the sort of off-gas grid regulation in the late 2020s, which was flagged in the Clean Growth Strategy in 2017 and is supposed to be followed up on in the Heat and Building Strategy. But again, we don't know what that will look like. So the sort of policy framework's fairly bare at the moment in terms of driving, you know, going from 30,000 heat pumps a year at the moment to 600,000 a year, as they've stated in the 10-point plan. There's a bit of a chasm.